All right, everybody, let's get started. How did a revisit of truss analysis go? Was that a valuable exercise on Wednesday? Everybody feels comfortable with trusses, hopefully. A little bit of Blackboard logistics. So in order to accommodate 6-2 being a bonus assignment, I had to do a little bit of adjusting on how it calculated the homework average. So I think I got it taken care of, but if it didn't get taken care of, I will fix it. What was happening is I was testing it out. I was trying to add a bonus assignment, and what it was doing is I threw in some like dummy terms. It was turning people's homework averages from like a 90% to a 4,000%. And I'm sure you're like, I'm okay with, yeah, I'm sure, you know, but like, don't worry about it, Dr. Mike, we'll live with it. The new version of Blackboard handles it a little differently. I think I got it taken care of, but I'll give you your bonus points. I just wanted to give you a heads up in case it reports something a little weird. I'll get it taken care of. Okay, one last time. Everybody good on trusses? Okay, today what we're going to do is we're going to discuss our other structural analysis topic, which is the construction of a shear and moment diagram. And so just a little bit of context so that everybody is kind of aware of what's going on. And I'm just going to sort of make a really quick point here on the board. We'll do a truss like this. This is enough. Okay, so let's say we have a truss and I put some loads on it, a load here, what have you. And I figure out that this member right here, let's just say this member, experiences 30 kilonewtons in tension, okay? The thing about this result, and one of the things that we really didn't discuss about trusses because it was sort of inherently baked into our assumption, particularly that we apply forces at the joints and that it's only axial load, is that it's 30 kilonewtons everywhere along the member. Like it's 30 kilonewtons here, it's 30 kilonewtons here, here. No matter where I look, the member is carrying an internal 30 kip response everywhere, which is perfectly fine from an assumption physics type standpoint. I mean, if I have a rubber band and I yank on it, it's basically carrying the same tension everywhere along the rubber band, okay? But that is not the case for bending, okay? When you take an element and you bend it, okay, typically what you're doing is you're taking the element, you know, here's, let's say, a beam, and you're putting, you know, a load here, a distributed load here, you know, a load, I don't know, maybe at an incline or whatever, right? And so the bending or the response, whether it's being bent or being sheared or what have you, that response changes along the beam, okay? So here, like for example, if I told you, here's this member, so let's just look at this member, okay? And I said, plot the force inside the member. This would be a pretty boring plot because it would just be 30 kilonewtons. It would just be a constant plot across the entire member, right? But if I asked you to plot the bending, if you will, inside this beam, it would not. It maybe would do that, it maybe do that, you know, something like that. It would be a plot. It would actually have a plot with some information to it, okay? We have a name for those plots. We call them shear and moment diagrams, okay? So that's what we're going to talk about today, okay? Does that sort of set the stage for what we're talking about? Everybody kind of get the idea? All right. I'm just curious, has anybody in here before this topic heard of it? Has anybody ever heard of a shear and moment diagram? A couple of you maybe who worked in an engineering office maybe have heard this before. There are certain skills that when you graduate with an engineering degree, you just sort of need to be able to do. Like it's just sort of in the lexicon. We can talk about math and being able to take a derivative, being able to take an integral and all that. But when we get into engineering topics, you know, this is a very fun foundational course. Understanding what forces and moments are is critical to engineering. And some of those applied type problems are very critical as well. The construction of a shear and moment diagram is one of the most seminal problems in engineering, okay? It's also not very difficult. It's pretty straightforward. at least for the types of problems that we're going to be looking at in here. And for most simple problems, it's a pretty straightforward enterprise. But it is important, okay? And I want to discuss that with you and give you some comfort on how to do it, okay? So just so you are aware, I have here some images here. So this is a beam that's pretty complicated, much more complicated than we're going to do in here. This is what the shear diagram would look like. This is what the moment diagram would look like. And I'll admit, I pulled this slide from my structural analysis class. So I said, yeah, it's a useful tool for civil engineers. But really, mechanical engineers are going to use them as well, and even biomedical engineers. And I would say that any system that you design that has an element in it that's being bent, you are going to generate a shear moment diagram. I don't care what system it is. Okay? And so you're going to find that in mechanical and biomedical applications as well. Okay? So just to sort of like explain what's going on, the moment diagram is sort of a representation of how much the beam is being bent. Okay? So the higher up that you get, the more bending there is, the more like flexing there is. Okay? Whenever you look at the moment diagram, you'll see positive values and you'll see negative values. So if I have a beam, like if I have this table and I apply load on top, the beam will bend and it will sort of like smile at you. Does that make sense? Like the bending will sort of look like this and it kind of looks like a smiley face. Does that make sense? That's what's going on over here anytime the moment is positive. Anytime the moment is negative, the beam is bending downwards and it's sort of like frowning at you. Kind of get the idea? So you'll hear engineers say smiley face, frowny face, bending. And I mean, it's, you know, kind of a cute way of putting it, but there's actually some truth to it. So like a good example of negative bending would be a diving board. Right? So if you're standing at the end of a diving board, right, what does the beam do when it bends? It sort of like does that, you know what I mean? It sort of bends down, so it's kind of frowning at you. Does that make sense? Whereas if you just had, you know, like a, I don't know, like a system like this, and you just put a force like that, the beam sort of bends like this. It sort of smiles at you. Okay, so the positive areas on the moment diagram are where it's smiling, and this is where it's frowning at you. The reason why they're valuable is for design. So like in a moment diagram, what I would do is I would take the worst case scenarios, in this case, let's say 460, and I would say I need to select the beam, whether it's made out of steel or aluminum or whatever. I need to select a beam with a certain material and a certain size that's strong enough to resist that much moment, okay? So if you all take Engineering 216 or BME 302, I think it is 302, that's what you're gonna do in there is take like these results and how do you size an element to be strong enough to resist that much moment. Does that make sense? So this is sort of part one and that would be part two. So that's what a moment diagram is. A shear diagram is basically just where it plots the change in vertical forces, right? So like the idea is if you had a beam, for example, that had, I don't know, something like this and then that, like if I applied a load like that, that really wouldn't cause that much bending, but it would really want to shear that beam in half. Does that make sense? And so this shear diagram represents that change in vertical force across the structure. I don't use S's for shears because my S's look like 5s. So I use the letter V for shear because it's a change in vertical forces. Does that make sense? Okay. Now, you're probably looking at this, and those of you who are in like a calculus class right now, how many of you are in a calculus class? Okay, so you're probably thinking, okay, if I got to graph that, Dr. Mike, that looks like a piecewise function, and I got some parabolas and lines and constants. That looks like a crazy function to write out. And the answer is, it is. My sound effects, you gotta love them, all right? But what I'm proposing that we're gonna do is develop a graphical technique in order to be able to do this. Okay, so in order to get to that graphical technique, what we're going to need to do is adopt a sign convention. So this sign convention is going to come up in our derivation here in a bit. But really what it's there to do is to guide the process by which we develop our graphical technique. So the idea is this, okay? And I've mentioned this to you before, okay? If I'm sitting here on this table, right, and Ms. Humbard's got the samurai sword or the lightsaber, and apparently it's a lightsaber, and cut through the table, I'm going to fall down. And the reason why is because there's an internal response at this point, right? Now, it doesn't matter which section of the table that you look at. You can look at this side of the table or look at this side of the table. It's going to be the same response. But just like with trusses, it's going to be an equal magnitude in an opposite direction. Like, for example, if we look at the P force, right? On this side, it's yanking away from the member. This side, it's yanking away from the member. This P force would represent tension, right? Because when I'm cutting the section, it's yanking away from the section. Does that make sense? Regardless which way I look. So it's equal magnitude, opposite direction. Okay? Now what I'm saying is for trusses, we tend to assume tensile forces are positive. For shears and moments, these are the sign conventions that we typically use to represent positive response. Okay? And if you want a why answer to that question, like some of you might go, well, wait a minute, Dr. Mike, why don't we just flip this? And why don't we just flip that? Like, is there any magic to choosing it this way versus this way? My answer to you would be this. Not really, but the graphical technique that we're going to develop that makes constructing these diagrams really easy is much more intuitive if you go with this. Okay? Just trust me on that and you'll see what I mean. So far, so good? Okay. All right. Now, our goal is not to derive some ridiculous set of equations, although we could do that, and there are some instances in structural analysis where we need them. A common example is if we want to find beam deflections. We do tend to need those expressions, but I'm not really interested in that in here. Okay, that's more of a next semester challenge for you all in your mechanics courses. Right now, I just want to know what's going on. I want to know what the shear and moment diagrams are, because really what these shear and moment diagrams are a representation of the internal statics of the structure. And it's like this course is named statics or something. So that's what I'm interested in here. Okay, so what I'm interested in doing is plotting the shears everywhere, plotting the shear or the moments everywhere. Okay, and so we're trying to graph it. That's what we're trying to do. We're trying to develop a graph. Okay, so so what I'm going to do is I'm going to handle this with this beam. Okay, so I've got a beam. It doesn't matter how long it is, and it doesn't matter what load is on it. So I'm going to say it's got some arbitrary load on it. We'll call it W of X. Now I've got it drawn upwards just to go along with the sign convention here and here, like according to the axis. It's like a positive load. Normally the load's negative because we have a beam we're placing it down, but again, just to make the math a little easier. Okay. All right. How many of you all remember in calculus when you started to discuss like a dx element, right? So you would say, okay, I've got this function, right? And I'm going to say, all right, let's look at the behavior over a differential element that is dxy. And how wide is dx? It's tiny, right? Okay? So we would look at so what we're going to do is look at the statics response on this element that is super, 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 super tiny. Okay? And so what I'm going to do is I'm going to zoom in on this super tiny element. Okay? This is really, really tiny. Okay? What I am proposing is that if you zoom in on this element and take a look at what's going on, I propose that on that element, okay, you can say that because it's so tiny, I know we've got this variable load, but because the element is so tiny, I'm going to assume that the load is constant over that element, just because it's so tiny, okay? Does that make sense? Okay. All right, so what we're going to do is we're going to try and evaluate the statics, okay? Now, here's going to be my goal, okay? My goal is, so if you look it to the left and to the right, let's take the shears. I've got a positive shear and a positive shear. Positive moment, positive moment. But look at what's going from left to right. Like I've got a shear and a shear plus some increment. Moment, moment plus some increment. So what I'm saying is that from one side of the element to the other, there's a change. There's a change in the shear and there's a change in the moment. And I want to see if I can figure out what that change is, okay? Is everybody with me on that? I want to see if I can know from as I try and plot this, I'm going to plot it from left to right. So I want to know if I go from here to here, how much does the shear change? How much does the moment change? Okay, so here's my element. And how am I going to figure that out? Wonderful equations of statics. So let's look at sum of forces in the y direction. And what I did here for this slide is instead of writing it as an equation, I'm just setting it up as a table because I think it's kind of a little easier to follow here on the slide. So what I'm going to do is say everything that's going up and then everything that's going down equals 0, right? Because I mean the idea is if I do it this way, right? If I say, okay, the sum of the forces in the y direction equals 0, and I do it like this, basically what I'm saying is all my forces going up are going to be positive, and then all my forces going down are negative, right? That sum has got to be equal to 0. So basically what I'm saying is the forces going up have got to equal the forces going down, right? So I'll just draw myself a little table and say everything going up and everything going down. So here's my free body diagram. What do I have going up? Okay, I've got V going up. Okay, now look what I wrote here. I don't have W going up. I have W times dx. Why did I do that? Why did I do W times dx? It's the area, right? It's like a centroid calculation, right? Remember when we would have a distributed load, we would say the distributed load times the length to collapse that into a vector. Remember that? So that's what I'm doing here, and then I'm saying, okay, we got this going down. So we got V plus this going up equals V plus this going down. So these two terms have got to be equal to one another. Just subtract V from both sides. So I'm getting dV equals W dx. And what if we do the moments? Hold on. What if we do the moments? Okay? So the moments are a little bit more involved. What I'm going to do is sum moments. And remember, you can sum moments anywhere. I'm going to sum moments about the right side of the element. So if I sum moments about the right side of the element, I could ignore this shear because we'll say it's going right through it. So I've got an M plus dm going this way, and then an M going that way. And what do I have left? I have a V dx. So that's this shear times its moment arm going like this. And then I got the distributed load. Now, before you get all worked up as to how I developed this, how I did that, and basically all I did is I said the force times the moment arm. And what's the moment arm? From the left end to the centroid, so halfway over, right? But it doesn't really matter all that much, and here's why. When you evaluate it, you get a dx squared, okay? Remember, dx is a really tiny number. What happens when you take a really tiny number and you square it? You get a really tiny number, right? So much so that we're just going to neglect it and say it doesn't matter, okay? And what we get is a pretty simple relationship, okay? And so we can write that relationship one of two ways, okay? So, like, one way we can write it is we can say, you know, if we have, for example, dV equals W dx, okay? That could mean one or two things. One way to write it would say that the load is the derivative of the shear, right? That's one way we could do it. That is great for spot checking these types of problems. That's not great for what we're after. What we're after is we're given the load, we're trying to find the shear. So how do we find the shear? We integrate. Does that make sense? Like the idea? And similarly, moment is going to be the integral of the shear. Okay? Now, I am sure that some of you are thinking, Dr. Mike, you said this was going to be easy. You're throwing the curvy little s's at us. We are on this side of 3rd Avenue. You're lying to us. No, I'm not. Trust me. This is a lot easier than you would think. Okay? All right. So like I said, we have a relationship now between loads and shears and moments. And I'll tell you that what's going to be more useful is the integrals. Okay? Again, I want to be crystal clear. We're not going to be integrating. We're not doing that. But we are going to be doing what integrals are meant to compute. What are the two fundamental problems in calculus? Like, you have a curve, you want to find the slope of the tangent line, right? And then in order to find the slope of the tangent line, we develop a derivative, right? What's the second fundamental problem in calculus? Finding the area under a curve, right? And how do we find the area under a curve? With an integral. I propose what we can do is find the area under the curve without integrating. That's the graphical approach that I'm talking about, okay? It's going to be a lot easier than you think, okay? What is important, so like I said, we're not going to be doing straight up integration. But what we are going to do is pattern recognition, okay? Let me ask you a question. What is the integral of 4? 4x plus c. Don't forget the plus c. No, but in all seriousness, it's plus 4x, right? What's the integral of that? 2x squared. Okay. All right. Now let me ask it to you a little more generally. What's the integral of a constant? Like, what's the integral of a? ax. What's the integral of ax? Ax squared over 2. What's the integral of ax squared? Well, what is it? Ax to the third over 6, right? So I want to think about pattern recognition. Would a general way of saying this is that if I have a function that's constant, and I take the integral of that, I get a linear function. And if I take a linear function, I take the integral of that, I get a quadratic function. If I take a quadratic function, take the integral of that, I get a cubic function. Everybody with me on that? We aren't even going to get the cubic functions in here, so you don't have to worry about that. What I'm saying is we're going to be taking the integral of this, and all it's going to be is calculating areas. And this is going to be what we use as our conclusion. We're going to say that we're going to be given a load diagram, and then we're going to plot a shear diagram. Then we're going to take a shear diagram, plot a moment diagram. And we're just going to go from one to the other. See, between load and shear, I propose that the slope of the shear diagram is going to equal to whatever the load is. That's going to be more of a gut check to make sure what we're doing is correct. But the change in shear is going to equal the magnitude of the load. And how do we do that? That's just this. And between shear and moment, the slope of the moment diagram is going to equal the shear. And between 2 points, the change in moment equals the area of the shear. We're going to start this process of constructing shear and moment diagrams with point loads because it's the easiest thing to do graphically. Okay? So when you have a point load, here's sort of the pattern. When you have a point load, the shear diagram, or let's say you have a beam with a bunch of point loads on it, the shear diagram sort of looks like stair steps, okay? Because between the point loads, there is no load, okay? Now, if I have no load, if W equals 0, what is the integral of 0? What's that? Plus 0 plus C, right? So the shear diagram, so if you have a bunch of point loads, the shear diagram is a bunch of constant functions. So the moment diagram is a bunch of linear functions. Does that make sense? And I think what would be best is let's just do one, okay? Let's just do one to see how it works, okay? So I want to look at this beam. And by the way, I am not a fan of just doing the same thing over and over again. We did this problem already in this class. I gave you this beam when we first started doing reactions, and we've already computed the reactions. So are you okay that I just gave them to you as opposed to chugging them out? Because if you don't, I think it was our very first reactions problem. Let's go back in time because I'm feeling nostalgic. Yeah, this is the same problem. Reactions example 1. So we got AY is 35.8, BY is 32.2, and that's what we're doing here. Okay. So far so good? All right, so let me show you how this works. So the first thing I'm going to do is I'm going to draw a series of vertical guidelines, and that's mainly to ensure that my artwork isn't all that sloppy. There's no rhyme or reason as to how many of these you need to draw, but basically what I do is I draw one for every what I call important point, okay? So let's strike a line, okay? And what we're gonna do is we're gonna do the shear diagram first. I'm gonna draw that in red. And we're going to say that the shear diagram is going to be in kips, okay? Now, basically what we're going to be doing with the shear diagram, how are we going to get the shear diagram? We're going to graphically integrate the load diagram. And you might go, how do you graphically integrate this? I'm going to give you a simple answer. You just do what the beam tells you to do, okay? So what do I mean by that? I start over here at the very, very left. And I say, okay, let's start at 0. And I look at the beam, and the beam tells me, it says, hey Greg, go up 35.8. So I'm at 0. I jump up 35.8, okay? So that puts me at 35.8, okay? All right. Now, let me put some labels up here so that we can all sort of speak the same language. We'll call this point C, D, and E. How much force is between point A and point C? It's not really a trick question, but it may sound like it. How much force is between point A and point C?
0.
Nothing. If I integrate nothing, what do I get? Plus. So I need to draw a function between A and C that has no slope. What does a function look like if it has no slope? Horizontal line. So my shear diagram looks like this. And then the beam said something to me. It said, Greg, hold up. Go down a little bit. Go down 20. So let's think about this. If I'm at 35.8 and I go down 20, what's that put me at? 15.8. Okay? Between C and D, how much load? None. No slope. So now, what did the beam tell me to do? Go down 30. So if I'm at 15.8 and I go down 30, what does that put me at? Negative 14.2. Okay? Between D and E. And these, it sounds like you're just asking the same question over again. During our next lecture, we're going to have load between, so we're going to have to discuss how to handle that. We're going to have distributed loads. But between here and here, nothing. So what happens now? I drop down to what? If I'm at negative 14.2 and I drop down 18, what does that put me at? Negative 32.2. And then what happens? It started at 0 and it ended at 0. Why did that happen? Why did the beam start at 0 and end at 0? And there is a very simple answer to that question. Because it's in equilibrium, and equilibrium states that the sum of the forces in the y direction must equal 0. So in an interesting way, a shear diagram serves as a check that when you computed the reactions, you got the right answer. But we're not done, okay? Because it is still possible that we computed reactions that were incorrect, but we still started at 0 and ended at 0. Why? Because we haven't looked at the moment diagram. Let's look at the moment diagram. How do I generate the moment diagram? I integrate the shear diagram. But what is integration if just finding the area under a curve? Okay, let's keep this real simple. Okay, real simple. All right, what is the area under this first rectangle? What is the area under this rectangle? How tall is it? Times 6, right? Because it's 6 wide. And what is that? I'm going to call it positive 214.8. By the way, what would the units of that area be? Foot, kips, or kip feet, and isn't that a moment unit? And that's what we're doing, right? So you told me 214.8. Okay. What about the next one? What's the area of this second rectangle? $15.8 times 9, and what is that? Second? Okay. What about this one, this third one right here? We're going to do the same thing. Okay. What this 14.2 times 7?
Negative 99.
Both use, yeah. So negative. And what about this last one? 32.2 times 8. Okay. So let's be clear. Those blue numbers are moments, right? And they are integrals of the shear diagram. Help me out with something. Add up these four numbers. What is that plus that plus that plus that?
0.
It's 0. Why? What are those areas? What did we say they are? They are moments, right? And I seem to remember that in static equilibrium, the sum of moments must be 0. This is the other check that those reactions are indeed correct, right? Because this reaction of 35.8 and 32.2 are the only two reactions that could guarantee both a start at 0 and end at 0 and positive areas equal negative areas. The only ones that can do it. What do you think? So far so good? Okay. So the next thing that you do is you construct the moment diagram, okay? So I'm gonna in case you were wondering when the musical interlude was going to happen. I know, I'm a dork. Okay. Okay, so we strike a line, okay? And so that line just here where that's like our x-axis, right? Okay, so we're going to draw a moment diagram. In foot kips, okay? We handle this the same way that we do the shear diagram. We basically just do what we did in the shear diagram. We just take it another step, okay? All right, so we start at 0, okay? But I'm gonna start asking some different questions, okay? So by the way, let's put those labels that we had put before. We said that this was A and B. We said C, D, and E. Just so that I don't have to keep scrolling up and down. Okay? So between A and C, is there shear on the beam? The answer is yes, right? There is a shear of 35.8, so there is something on the beam. So that means something's got to happen between here and here, okay? The first thing I want you to do is pay attention to the areas, okay? So let me do this. So tell you what, let's just construct the moment diagram and then let's make some observations about it later, okay? I'm going to pay attention to the areas. I'm going to start at 0. I'm going to jump up to 214.8, okay? Now, I propose that the path from here to here is a line. It is linear, okay? It is linear because the shear is constant. And if you integrate a constant, you get a linear function, right? Isn't that what we said? So the moment is linear. Okay? The next thing that we're going to do is we're going to start at 214.8. So if I'm at 214.8 and I jump up 142.2, what does that put me at? So if I'm at 214.8 and I jump up 142.2, where am I at? $357. And I propose this is also linear. In fact, all the segments are going to be linear. Okay, now if I'm at 357 and I drop down 99.4, what am I at? 257.6, and then I drop down to 0. All right. Now, before we move on, let me just point blank ask a question. Was this hard? It's easy, right? Again, the construction of a shear moment diagram is not hard, but now I want to have some meaningful observations about this. Okay? I want to go back to these derivative and integral relationships, and I want to start asking some meaningful questions. I don't want anybody to do a single calculation. I don't want anybody to touch their calculator, but I want somebody to see if they can tell me what is the slope of that line.
214.8 over 6.
You're doing calculations.
35.
Say it again. It is 35.8 because the derivative of moment is the shear. The slope here is equal to the value there. Remind me, when I graph a line with a positive slope, it's an uphill, right? Right? So, what's the slope of this line?
15.8.
So, okay, all right, 15.8. I seem to remember from my algebra class that what's the difference between a line with those two slopes? This one on the left is going to be a little bit steeper than that one, right? Isn't that what happened? So, is this slope negative? Is the value on the shear diagram negative right here? Ooh. See? You start to see the pattern here? This slope and this slope is negative 14.2 and 32.2 respectively. You see what I mean? That you don't need to do the math, right? Because it tells you what it is. And I like the fact that shear and moment diagrams done properly do serve as a check of the statics that you've done. Because if you computed the incorrect reactions, it would not start at 0 and end at 0. You wouldn't have the sum of the areas equal 0. It wouldn't work like that. You see what I mean? So it's a really cool enterprise that it checks itself in that regard. Okay. Does anybody have any questions?
So could you like interpolate from your moment diagram there and just find the moment about any arbitrary point?
Yes, yes. So the question was like, what if I wanted to find the moment right here, right? Okay. So there are two ways of doing it. One way of doing it is to do what you said, interpolate. Okay. The other way of doing it is to cut a section and actually write the equations of equilibrium. You'll get the same answer. Same answer. What's going to be interesting next time on Monday is what happens when the distributed load is applied to the beam. So what we're going to have is a linear load, or sorry, a constant load, a linear shear diagram, and a quadratic moment diagram. So we're going to have some parabolas on the moment diagram, okay? But I wanted to keep it easy, and then we ramp it up a little bit next time. Does that sound good? Any questions? Then I will see you all on Monday. I'm going to let you out a little early.